Hello, guys. Welcome back to MedZone African Motives. We are still working on our electrotechnology N3, and this is the revision that we are going to have on the AC theory, working on the three-phase systems. So you need to understand typical exam questions, how your questions are going to be given in terms of a three-phase. So this is a 25 kilowatt three-phase, take note, it's a three-phase induction motor. So we're going to talk about that. Then the connections that we are given about this motor is started by means of a star delta starter. So we've got two things there, the star and the delta. These are the things that you're going to need. As you can see, there are questions on a star, questions on a delta. This is because we are considering two things in common to be connected together. Remember that in our connections, or in these three-phase connections, we can expect to have a star connection. All right, let me just summarize what exactly we're gonna expect. So remember, we're gonna just have our coils in this case. All right, so that is another part of our three-phase. All right, so these coils that are being connected from the live wires. So we've got the red, the yellow, and the blue. All right, so this is the line current that is we are having. So we've got the line current, all this part. Okay, so I'm not gonna talk about much, but what we need is the relationship that is going to be happening between these phase voltages, the voltages that we are having at a phase. There's a phase voltage, the phase voltage that we are given, and the voltage that is referred to as the voltage across the line. What is the relationship that we're gonna consider? All right, so this V voltage that we are given here is the voltage of the phase. Meaning to say, again, we're going to have the voltage here for Y, the yellow, again, for blue. These are voltages that we are considering to be in a phase. So what is the relationship that we are going to have in this star connection? The voltage across the line, it is equal to the square root of 3 times the voltage across the phase. Each phase that you're considering, all right? So you're going to use the square root of 3 to consider that. But for the line current, we are going to see that the line current is equal to the phase current in a star connection. We are going to have the line current being equal to the phase current. All right. Then in a delta, we are going to have another part. So guys, here I'm just giving you a sketch. All right. I'm just giving you a sketch of what you are supposed to consider. All right, so remember in your delta, we are going to have this time our coils connected like this. All right, so we're gonna have another part here. All right, then we're gonna have another part. All right, so we're gonna just consider something like this. So this is what we are given, whereby we got the voltages across the phase. This part, the voltages that we consider across the phase, the voltage that you consider as the line voltage, the line current in this case that is entering so many things that you're gonna talk about. All right, but in this case, I want you to understand at the end what is the relationship that you consider in a delta in terms of the voltages, in terms of the current. The line voltage is equal to the phase voltage this time. And the line current, it is equal to the square root of 3 times the phase current. That is the relationship. That is the most important part that you need to consider. So in your formula sheet, as you can see, we are given on number 38, the relationship that we have in this case of the VL equal to VP. This is for a delta, as we can see, that is for a delta. And the other relationship that you are given here is for a star connection. So this is what we have. That is what you have according to your formula sheet, okay? So meaning to say, guys, you are limited. You are not told that this is for delta, this is for star. You need to know that. you need to know your formulas, memorize, understand your formulas at the end. All right. So this is the major part that you're going to consider between the two, because these are two things. All right. Now you're given that this is a 25 kilowatt, 3-phase induction motor. Okay. Whenever we are given this type of a question, a 25 kilowatt, 3-phase induction motor, at 50 kilowatt, this kilowatt, the power that you are given as a certain power, it represents the output power. So this is your P out, not input, but the output. So be careful on how this is supposed to be taken. So there, according to the information that we are given, we have got the output power, which is the 25 kilowatt. All right, so let us consider again what we have. So this is a 3-phase. Okay, so we consider in a 3-phase induction motor. So meaning to say it is inductive. Okay, is supplied from, so this is the voltage, the supply. This is your line voltage, okay, at a frequency of 50 hertz. So there we have got the line voltage, all right? We've got the line voltage of 525 volts at a frequency of 50 hertz, at a frequency of 50 hertz. Remember, we are given that this is a 3-phase connection that you're going to have. And we are also given that, and it operates at a power factor of 0.8 lagging, since it is an inductive, and the efficiency being 85%. So we have got the power factor of 0.8 lagging. Then we also have the efficiency of 85%. So divide by 100, that's 0.85. Okay, so this is what you're given. And we are given that this motor is started by means a star delta. This is where this part plays a role, where I was talking about the relationship between the star and that of a delta. Okay, so the question is, calculate the following. 7.11, the phase voltage of the motor when its windings are connected in star. They are connected in a star connection. So this is it, guys. In a star, what is the relationship between the voltages in a star? We saw that VL, which is the line voltage, is equal to square root of 3 VP. This is considering a star connection. We are in a star connection, all right? So that's in this case of 7.1, we are considering this to be connected in a star. And in a star, the line voltage is equal to square root of 3 phase voltage. What is it that you're asked to calculate the phase voltage? So you can divide by the square root of 3 to determine the phase voltage at a line voltage of 525 volts. So that is the idea there. All right, so this was going to give you phase voltage of 303,109 volts. So that is the idea in this case. All right, then let us check 7.2, which is the other part of our question. The phase current of the motor when its windings are connected in a star. We are still in a star, and in the star, we saw that in terms of the current, the line current and the phase current are the same. All right, so this is what we have. These two are the same. So, but what is the idea there? Remember, we want the phase current, but we know that the line current and the phase current are the same in a star. So the question is, where are we going to have either of these, phase or the line current? If we were having the input power, we can calculate the line current, because the relationship states that the input power is equal to, there we're talking of the power, the true power. So that is the square root of 3 times the line voltage times the line current, the cos of theta. If you consider in terms of the phase, it will be 3 times the phase voltage times the phase current times the cosine of theta, which is the power factor. So you can use any part that you want. It's either you're going to work with the phase You can work with a line. So in this case, if you check, yes, we calculated the phase. We can use that, any part that you want. So this is any way that you're going to consider. But in either case, if you're to consider we do not have the input power that can help us to calculate either the phase or the line, which is the same. In this case, remember I said these two are the same. We have got the line voltage, the phase voltage, the cos of theta, that is the power factor. The power factor represents the cos of theta. But we do not have the input power. So where are we going to have this? That's the power output and the efficiency. That's where they play a role. What is the relationship between these two, the efficiency and the power output? Remember, the efficiency is equal to the output over the input. That means you are referring to the power output over the power input. So by making the input the subject, you can just cross multiply. That will be efficiency times Pn is equal to P out, then divide by the efficiency both sides so that I remain with the input power. That is the output over efficiency. So that's it. So the power output, remember, a 25 kilowatt, that's the power output. Do not confuse that. So this is 25 kilowatt. That is 25 times 10 to the exponent of 3 over the efficiency. Remember, it was 85%. That's 0.85. So this was going to give you the input power, which was going to be 2,000. It was actually 29,411.765. So this is our input power. Remember, the purpose of calculating the input power is that we can use it to determine the current. So it is up to you. You're going to use this formula or you're going to use the first one. All right, so let us consider this first formula that you are given. So on this formula, I'm going to make this the subject, the current. Remember, we said these two are the same. So if we are to make the line current the subject, it means we are going to divide by the square root of 3 from the input. So it's going to be input power over, you divide by the square root of 3. Okay, you divide by the line voltage, you divide by the cos of theta. Remember, what you need is this. So you're going to divide by every other part so that you remain with the current. So this was going to be the input power, which is the one that we got. Remember the value that we got on our input power. So this is going to be the substitute to 29,411.765 divided to the square root of 3. Remember, we are under a 3 phase. So the square root of 3 is supposed to be there. All right. Remember our line voltage, it was 525 times the cos of theta, which is our power factor of 0.8. So remember your power factor, that is 0.8. So this was going to give you a current of 40.431 amps, which is representing the line current. But as we know that in a star, these two are the same. The line current and the phase current are the same, as we are being asked to calculate the phase current. So therefore, phase current is equal to 40.431 amps. These two are exactly the same in a star. So you must know your connections. You must understand how these connections are given or presented. So in the same sense, like we saw that we can also determine this from this very same power formula. From the same power that we have, but using the phase, just because these values are rounded off figures. But let us see if we were to use this formula, if we were to consider the second formula, it means you were going to divide. This one is exactly having the phase current. So it means the phase current is going to be the input power over, you divide by 3, the phase voltage, the cos of theta. All right, so this is going to be our phase current, and this is giving us direct the phase current but you must take note when dealing with the phase, you multiply by 3. When dealing with the line, you use the square root of 3. The input power is not changing. It's still the 29,411,765. Okay, this is over 3 times the phase. When we're dealing with the phase, it was 303,109. All right, that is 303,109. That is our phase voltage. What about the phase? This cos theta, which is the power factor. Remember, power factor, that's 0,8. That's our cos theta. So you're going to use 0,8. So this was going to give us the phase current at the end. Let us just see, because of the rounding off of values, we are using this value being rounded off figure, this value being a rounded off figure. On this question, or on this one that we had before, it was only the power input, which was a rounded off figure. So we're just going to see if we're going to have the exact answer, or it's going to be something just a little bit different from what we have, just a little bit. Okay, so this is it. 29,411,765. Then we're going to divide by 3. Okay, sorry for that. So you're going to divide by 3 times 303,109. All right, times 0,8. So this is going to be 40, as you can see, that is exactly one and the same. You can also round off to 3 decimal places. That shift set up. You can fix this to 3 decimal places. That is going to be 40,431. So as you can see, we are obtaining exactly the same answer, just like what we had before. So that's 40,431 amps. So still one of the same thing. As long you consider, as long you use your formulas properly, you are not going to have a challenge in this subject, guys. You're not going to have any challenge in this whole topic. In fact, the whole subject at large. All right, 7.3. We are given to calculate the phase voltage of the motor when its windings are connected in a delta. So this time we are dealing with a delta connection. What is it that we are supposed to consider in a delta? Remember what I said in terms of the voltage is the line voltage and the phase voltage are the same in a delta. So meaning to say our line voltage of 525 is same as our phase voltage. So that is what we're given in this case. So 7.3, our line voltage and phase voltage is the same. So it means our phase voltage is simply going to be 525 volts. So this is the condition of a delta connection. All right, then the other part, 7.4, it was to calculate the phase current. All right, so this time is the phase current of the motor when its windings are connected in a delta. So if you consider, we already have the line current from the power that we calculated before. So it is simply going to be a continuation from the line current that you calculated before. That is why you see it just has 2 marks. But what is the idea that we consider in a delta in terms of the current? We saw that the line current is equal to square root of 3 times a phase current. So the question is, where are we having this? That is the question. Are we having the line current? All right, we have got the line current, guys. Where are we going to have this? If you consider when you are calculating in this connection before, when we were considering a star connection, this was the line current that we had. This is the line current, guys. This is the line current that you're having. And this is affecting our motor for the line current. But in a delta connection, it is now considered that this is no longer the same. So that is where we are going to consider our formula to say we are in which connection. But the line current that we have we are going to take that line current that we calculated before. That was 40,431 divided by the square root of 3. Remember, that was the line current taken exactly from the power, from the input power. So that one is going to be the same line current that you use in your calculations. All right, so that was going to give you the phase current to 3 decimal places. That was going to be 23,343 amps. So that is how you can calculate these typical questions. You just have to be careful. The formula to use. Then the reactive power of the motor, which is on 7.5. You want to calculate the reactive power. So as we are to consider that we are in a 3-phase, we are working with a 3-phase. We are working with a 3-phase. So if you do not want to have challenges, work with the line voltage and also the line current that you're given. But remember that as long you are dealing with a 3-phase, there is a 3 to be considered there. But how is it considered when you are calculating the reactive power? So the reactive power, it was supposed to be V voltage times current times the sine of theta. But under a 3-phase, it will be the square root of 3. Take note, the square root of 3. Then the voltage, the line voltage times the line current times the sine of theta. So you can also consider this as, you can also consider as 3 times the phase voltage times the phase current times the sine of theta. This is another way that you can also consider your formula. So just try and see. So using the first formula, we need the theta. This is the cos of theta, not the sine of theta. Power factor represents cos of theta, not sine. So meaning to say from the power factor, we are going to determine the theta. So find theta from the power factor. All right, so this is taken from the power factor. So the power factor, remember, it represents the cos of theta. So if the cos of theta is equal to 0.8, which is our power factor, what about theta? So in this case, our theta from our trigonometry, how do you write cos on the other side? It will be arc cos of 0.8. Remember from your mathematics. So that is arc cos 0.8 to represent the angle. That is the angle that you're talking about there. So this is your mathematical, guys, calculation shift cos, that is arc cos of 0.8. So that is going to give us, remember, I fixed my calculator to 3 decimal places. So it's going to be 36,870. So that's 36, okay, 870, which is just 0.87. Okay, you can just write the 0, no problem. We just need the angle, guys. All right, so from this, we can now calculate the reactive power since we have got the angle. Remember our line current, we calculated this before. So Q, using the first formula, it is going to be square root of 3 times the phase, the line voltage of 525. Remember the line current, when we calculated this, our line current here, it was 40,431. So that is 40,431. That was our line current. All right, so that is it. So you're going to have the sine of theta, which is the sine of the angle that we calculated. So that is the sine of the angle we calculated here. That is times the sine of 36,87 degrees. Okay, so that is going to be the reactive power. In this case, we're going to obtain 22,059,045. Remember, this is volt ampere reactive. But as we understand, we can also write this answer in kilo volt ampere reactive. So how do we convert to the kilo? You just divide by 1,000, divide by 1,000. That means your answer is going to be 22,059. So this will be kilovolt ampere reactive. So this is how you're supposed to have obtained your reactive power from the power factor. You need to calculate first the angle theta that you're going to use. So these are the calculations that you're going to have under the three phase. So it can be a combination of the two, like what we have, the star and the delta. So we shall have more questions to come from Mason African Motives till we meet again.